In this section, we're going to be talking in detail about the periodic table. The first thing for you to know is whenever you look at one element, there are a couple of numbers that go along with the atomic symbol for that element. So for example, if you see at the top left corner of this slide, you have 19K and 39.0983. The 19 represents the atomic number, which is the same as the number of protons. K is the atomic symbol for potassium, and the 39.0983 is the atomic weight. And in the last lesson, you learned how to calculate atomic weight by finding the weighted average of the atomic masses for the different isotopes of potassium. A couple other things for you to know. The periodic table, the rows, we call them periods. So when we look at trends later on in another unit, we will talk about the horizontal rows. We'll refer to them as periods, while the vertical columns are called groups. So you can see group 1A, 2A, 3A, 4A, 5A, etc. as you move across the periodic table. Those are the vertical columns. The important thing for you to know by looking just at the periodic table, if you notice what I have provided and what's in your textbook is color-coded. What's in your notes is not. So if you would color in right now, you can pause the video. The beige color, those are metals. The green color, those are nonmetals. Notice they are to the right of the ladder. And then on the ladder are purple elements, including boron, silicon, germanium. And as you go down that ladder, you'll see all of those purple elements. Those are your metalloids. And I'll talk about the difference in a second. But pause me for 1 sec. Do notice that hydrogen, which is on the top and far left, that is actually a nonmetal, even though it is to the left of the ladder. So color those in. Now, the important thing for you to know about metallic elements, the ones that are to the left of the ladder and that make up the majority of the elements on the periodic table, their properties include the fact that they are lustrous, meaning they're shiny, they are good conductors of electricity, and then also that they are solids at room temperature. Nonmetals are either gases, solids, or liquids at room temperature, so there's a lot of variety in nonmetals, while metals, there is less variety in their characteristics. And then metalloids, which are between metals and nonmetals, their characteristics are between those of metals and nonmetals. So some are fairly good conductors, not as good conductors of electricity and heat, not as good as metals, but not as bad as nonmetals. The next thing that we're going to be talking about is molecules, and specifically molecular compounds. The important thing for you to know about these is that they are created by two or more non-metal atoms, and the reason why they form, the attractive force that brings those non-metal atoms together, are covalent bonds. In covalent bonds, electrons are being shared. We're going to look at those in detail in another unit, but the important thing for you to know is that electrons are shared. They are not donated like in ionic compounds. Okay. There are two different terms that we will use when talking about molecular compounds. The first is the molecular formula. Now, the molecular formula, that shows how many atoms there actually are in the molecule, while for an empirical formula, it just indicates the relative number of atoms. An easier way of imagining this is that it's just the smallest possible whole number ratio of atoms. So I'm going to show you an example right now to compare molecular and empirical formulas. This right here, C2H4, if you notice, this is not the smallest whole number ratio because you can reduce the 2 and the 4 to a 1 and a 2. So this is the molecular formula. What this is telling you is that there are 2 carbons and 4 hydrogens in this molecular compound. It's showing the actual number of atoms. This, CH2, is the empirical formula because it is the smallest possible whole number ratio. You can't reduce that further. The important thing for you to know, CH2, it's possible that not only could that be the empirical formula, it could also be the molecular formula, meaning in that one molecule there's only 1 carbon and 2 hydrogens. The empirical formula could not be C2H4 because you can reduce it. If you can reduce it, it is not the empirical formula. Next, since we just talked about molecular compounds, I'm going to be talking about ionic compounds. Atoms can either gain or lose electrons, and when they do this, they become ions. Now, If an ion has a positive charge, we call it a cation, while for a negatively charged ion, we call that an anion. If you look right here, this is a sodium atom. What happened to it from going from left to right is that it lost one electron. So if you lose one electron, which is negatively charged, it actually has a positive one charge, and that's represented with the Na+. In this case, chlorine had 17 electrons, but then it has 18, which means it gained one electron, which means it would have a negative charge. So the sodium ion is called a cation, the chlorine ion is called an anion. Metals, which we'll learn about later on why they do this, but they tend to lose electrons to be cations, as you can see on the left-hand side, and nonmetals tend to gain electrons to become anions. The interesting thing for you to know is that the chemical properties of these ions are very different from their atoms. So for example, a sodium atom, if you leave it out in the open, it will react violently with the water in the air, while Na+, the ion, is something that we eat every day in sodium chloride. So sodium atom and the sodium ion are very different. One is very reactive while the other one is not. This should be review from chemistry. If you look at the periodic table, it provides us with the opportunity to predict what the charge of ions are going to be. What I would like you to do right now is go back to the first page of your notes and write this in on the periodic table. In this first group, the 1A group, all of those atoms will assume a +1 charge when they become ions. So they have a +1 charge. Okay? For group 2, they have a +2 charge. Okay? For group 3, we'll just talk about aluminum, but aluminum has a +3 charge. Then if we skip over for the 5A, nitrogen, when it becomes an ion, has a -3 charge. All of the group 6 have a -2 charge, and then the 7A have a -1 charge. The reason why this is the case is because if you look at 1A, all of those atoms have one valence electron, and we'll look at that later on. But since they have one valence electron, they want to lose that one electron to assume the electron configuration, which again we'll review as well, of a noble gas. The group 2 metals want to lose 2 valence electrons, so they have a +2 charge. If you look over at nitrogen over here, it has 5 valence electrons, so all it has to do is gain 3 electrons to get the electron configuration of a noble gas, so it has a -3 charge, oxygen -2, and fluorine -1. When we're talking about ionic compounds, unlike molecular compounds in which electrons are shared and the atoms stay together in one molecule, what happens in ionic compounds is that when electrons are transferred, the positive and the negative ions are strongly attracted to each other, and they create this 3D shape, which you can see in figure in letter B. And so it's no longer one Na and one Cl. Instead, it creates this three-dimensional crystal in which, as you can see, sodium is surrounded by chlorines because all of those negatively charged chlorines are attracted to the positively charged sodium. Okay. A couple important things for you to know. Ionic compounds are neutrally charged, and so that's going to help us to write the formula for the compounds. The important thing for you to know for ionic compounds, we only write the empirical formula of the compounds because they match up, the positive and the negatively charged ions match up perfectly together. You don't have doubles of an atom like you do with a molecular compound. Instead, it's a 1-to-1 or a 2-to-1 relationship, which you will see in 1 second. Okay. So for example, if I have magnesium and nitrogen, in order for that compound to have no charge, magnesium, we need 3 magnesiums and 2 nitrogens. What I like to do is I cross my charges. So since magnesium has a +2 charge and nitrogen has a 3- charge, the 3 becomes the subscript for magnesium, the 2 becomes the subscript for nitrogen. If I were to do this math to check to make sure Mg3N2 was neutral, was a neutral compound, since magnesium has a +2 charge and there are 3 of them, that's a total of +6. Nitrogen has -3, since there are 2 of them, that's -6. So +6, -6, that is a neutrally charged compound. So what I want you to do right now is, there are 3 problems for you to do. I'm going to work on the first one with you, sodium sulfide. And then you're going to do write the formula for aluminum oxide and for magnesium fluoride. For sodium sulfide, sodium has a +1 charge and sulfur has a -2 charge. And we'll look at why it's an IDE ending in a second. So since sodium has a +1 charge, sulfide has a -2 charge. When I cross my charges, the formula becomes Na2S. Now that we've learned how to write the formula for ionic compounds, we're now going to learn how to name those ionic compounds. The first step is writing the name of the cation. Now, cations are formed from the metal atoms, and they have the exact same name as the metal. Okay? If a metal can form cations with different charges, which refers to the transition metals, not group 1, group 2, or group 3 metals, but the transition metals, then we have to use a Roman numeral in parentheses to indicate the charge. For example, since sodium always has a +1 charge, we never need to write the charge of sodium because we always know it's +1. But for example, if I have copper, it could have a +2 or a +3 charge. So in order for someone to know which copper ion I'm referring to, I need to include a Roman numeral in the name. So that's for the cation. Okay? So for example, if iron has a +2 charge, I would write iron 2. Or for iron with a +3 charge, it would be iron 3. And that's just for cations for whose charge I do not know all the time. So for example, the fact that iron could have a +2 or +3, copper +1, +2. When I'm writing the anion, all I have to do is I replace the ending of the name of the element with IDE, and that's just talking about a monatomic anion. So for example, Br, instead of bromine, becomes bromide. Oxygen becomes oxide. So for example, if I have CaF2, calcium always has a +2 charge, so I'm just going to write calcium. Then for fluorine, I need to write it with an IDE ending, so the final name for this, the nomenclature, is calcium fluoride. So please do these examples right now. Not all anions are monatomic anions. You also have what are called polyatomic ions. If you look at this list, you should be familiar with most of these. The only new thing is that for the AP test, you need to have these memorized. So what I would recommend doing is going on to Quizlet, and there are a lot of different flashcards that have already been made for you to practice these. If you notice, I'm just going to go through a couple of these. If you have an OH with a -1 charge, that the name of that polyatomic ion is hydroxide. NO3- is nitrate. If I lose one oxygen, it becomes NO2-, and the name of it is nitrite. So you're not going to be memorizing all of these, because if you memorize nitrate as NO3 with a -1 charge, you know nitrite just has 1 fewer oxygen. For example, if you look at, let's look at chlorine, if you have ClO4 with a -1 charge, that has 1 more oxygen than normal chlorate does, therefore its name is perchlorate. If it has 1 fewer oxygen, ClO3-, it's chlorate, even 1 fewer oxygen, chlorite, and then if it has 1 fewer than chlorite, it becomes hypochlorite. Okay, so I'm going to be using these when we're naming. You can start by using this table, but you will not be provided it on a quiz or test, and you will be quizzed on these polyatomic ions. So for example, if I'm given Na3PO4, I start off and I know that sodium always has a +1 charge, so I don't need to include the Roman numeral for its charge. And then PO4, since it is not a monatomic anion, it is a polyatomic anion. I need to look it up, and PO4 is actually phosphate. So you just write sodium phosphate, and that's the name of that ionic compound. So do the rest of these, please.